Okay, so for this problem, let's calculate the reaction forces at A and B. So we just review that and then try and plot the shear and moment diagrams. So assuming it's pivoted at A, what are the clockwise moments? We look along the beam and we add up all the forces that are going around clockwise. So here's our pivot. So that's going around clockwise. The UDL is going around clockwise. The 5 kilonewton is going clockwise. So is that, and so is that. Okay? The only one that's going anti-clockwise is that. So the clockwise moments are given by all of those downward forces. So we multiply the force by the distance from the pivot. Put each one in the bracket. 8 times 2 plus the 1.5 kilonewton force. This can be replaced with a point force acting there with a value of 1.5 kilonewtons per meter times 5 meters is 7.5 kilonewtons. So that would be 7.5 times the distance, which is 3. So it's this distance, the 3 meters, plus half of this distance. So 3 take away 8 take away 3 is 5, so it's 3, 5.5. So 5.5 to the middle of that. Okay? 5.5 plus 5 times 10 plus 12 times 12 plus 20 times 20 gives us the total clockwise moments. Okay? And then the anti-clockwise moments, so what does this come to? Add them all up, what do we get? 651.25. And these are measured in kilonewtons, so that's kilonewton meters. So that's the total and clockwise moment. So the anti-clockwise moment, the only one that's acting anti-clockwise moment is the reaction at B. So reaction at B times 16. So therefore, clockwise moments equals anti-clockwise moments. So 16 RB equals 651.25. Therefore, RB equals 40.7 kilonewtons. So once we've got RB equals 40.7 kilonewtons, we could then pivot it at B, so this would be a good idea, and then some clockwise moments. Now this is the awkward one. So there's my pivot. That's going around clockwise. And the reaction at A, which is given by this, that's the reaction at A. That too is going around clockwise. So the reaction at A and the 20 kilonewton force will be my clockwise moments. And then all the others are going around anti-clockwise. So I'll leave you to finish that off and check that you get the right answer. Okay, if you're not sure, just practice it. But we end up with a value. So similarly, RA equals 11.8 kilonewtons. Okay. So we've got those values and you can check yourself. So now we can transfer this information to our diagram. We've got the reaction forces at A and B, and we can draw our shear force diagram. So I'm going to pause this for a second and you plot it. And if you've done it correctly, you should find it reaches 0 by the time you get to the end. You can see our shear force diagram. Note that it starts and ends at 0. Note also that there's a couple of points at which we've got maximum bending moment. here, at this point, maximum bending, and at this point, maximum bending. So we've got a couple of points at which we should end up with maxima on our bending moment diagram. Still, we should find, by the time we've finished, that the total area above the axis equals the total area below the axis. So now we can start plotting out our bending moment diagram underneath. All values are going to end up not necessarily above the line this time. We might have some moments going the other way because of the fact that the pivot is not either end. So we could end up with some negative moments here. So we need to make sure that our construction lines allow us to go below the line as well as above. Okay, so let's look at it. So, right, the bending moment is positive. So the value of the gradient is given by the value of the shear. So it starts at 11.8, positive gradient, and it's going to go up until it reaches a value for the moment which is given by the area underneath this first rectangle here. So we calculate that area, and that will give us the bending moment at this point here. And then, because it's the shear between those 2 points is the same, we'll have a constant gradient, so it could be a straight line going straight up to that point. So if you could just calculate what that point is by finding the area underneath the curve. Now we have another positive increase in the moment. That's this area here. And so we find that area, and again it's going up, but this time the gradient is less. The gradient is only positive 3.8, so it will be a shallower line increasing to whatever that area is underneath there. Now we continue to increase the moment because this is a positive area. So we find the area underneath here and it increases up to that point. But this is UDL, so it's not, the gradient is actually reducing, but the value of the gradient is getting smaller down to 0. So we calculate the area underneath the curve. It's going to increase to that value, but then we need to think about how it curves. So have a think. Actually, because of this point is a point of interest, a point of maximum bending, we need a construction line down here. The question is, what is this point? And how do we find out what that is, what that point is? But we do know that the stress, which is what we're interested in, the stress is decreasing at the rate of 1.5 kilonewtons per meter. So I'm starting off at 3.8 kilonewtons, which is this point here, and then I'm reducing the value of the stress by 1.5 kilonewtons per meter until I get to this point here where it's 0. So how do I find the distance travelled? I divide the stress at this point, 3.8, by 1.5, and I'll end up with the distance I've gone, 2.53 meters. So the area underneath the curve now will be given by a half of 3.8 times 2.53. Area a half of 3.8 times 2.53, which is 4.81. So we need to go up by 4.81 because it's a positive. So we're going to go up to by 4.81 to get to 32.2. But how do we get there? It's not going to be a straight line because it's a UDL. Look at the gradient. This gives us a clue. So it's a positive gradient at this point. Remember, the gradient is the value of the shear. At this point it starts off with a positive gradient. So it's going up in this sense, and then by the time it gets to here, the gradient is 0 because the stress is 0. So it's going to start off going up and then level off. In other words, it's going to go something like that. Okay? We can now say what the value of the maximum bending moment is, and it's 32.2 kilonewtons per meter. And where does it occur? At a distance of 2.53 plus these two distances here, whatever that total distance here is. So we can say at what point in the beam bending moment, maximum bending moment occurs, and where. So now we start to come down because it's a negative area. So this is a negative area underneath here. Calculate the area, which is going to be 2.47, that distance from there to there, times by that distance, which is 3.7, negative. So we're coming down by that area, which takes us to 27.6. So we're coming down now to 27.6, which is the 32.2 minus 4.57, which is the area. But now, how are we coming down? If we look at the value of the stress at this point, look at the gradient, the value of the stress at these points. The value of the stress is negative and getting more and more negative. So it starts off with a shallow negative gradient and ends up with a larger negative gradient. So it must be coming down like this, getting gradually a bigger negative gradient. So safer territory at this point, we're away from the UDL, so now the gradient is constant, so it's going to be a straight negative gradient downwards of minus 3.7, that's this bit here, and the area under the curve tells us how far down we're going. So calculate this area and come down with a straight line to that point. So that takes us down a straight line to 20.2. So we've now got a larger 82.8, subtract from this takes us to, minus, that's 3.2 now, we've got to subtract 82 point something, gets us to minus 79, is that right? Minus 79.8. So we're going down to minus 79.6, minus 79.6 to here. So the final area takes us back to zero, positive moment. Okay. By following logic, we end up with our moment diagram, ends up at zero, which is what we expected. But we also find that because now one of our supports is not at the end, we actually end up with negative moments, or moments going the other way, which you probably would expect, actually, if you think about it. Okay. Notice here something else that's worth pointing out. At this point, which is not drawn very well, but at this point we've got zero moment. So that might be a point that we're interested in, and we could find where that is in the beam, because we know this distance from here to here, and if we were interested we could do a similar thing to what we did to find where the point of zero stress was here. At this point we could do a similar thing, because the gradient, we know the value of the gradient, it's the value of the stress, which is negative 20.7 at that point. So we're coming down at the rate of 20.7 from 3.2 at that point. So 3.2 divided by 20.7 will give us this distance, which is small. And so we could calculate exactly where on the beam we've got a point of zero moment.